Hello, I welcome you all on this course of thermal physics. As you're aware that we are doing this course on thermal physics, and let us start with the basic study of thermodynamics first, and let us also start with some very basics at first. Okay, so let us start with the basics of thermodynamics. Okay, okay. So okay. So the point is that in today's lecture, we are going to do a few basics that are important for thermodynamics. First, what is thermodynamics? Thermodynamics is an experimental science. It is an experimental science, and it is based on a small number of principles. So it is based on principles, and which are nothing but generalizations from our experience. Okay, so these are generalization made from our experience. Okay, that way I can say uh, that basically, uh, this kind of study, um, I can say it is a phenomenological science. So basically, I can say that because see, thermodynamics is based on what? Based on some empirical laws. So okay, it is based on some four empirical laws that we are going to study later on. Okay, in that sense, I say that thermodynamics is a phenomenological science. Okay, so basically, it means that the what you can say, the laws are derived from experience and they need no proof. And need no proof. Now, the point is, we have to make some initial definitions clear before we head on to the study of thermodynamics. Okay. So basically, we start with something called as thermodynamic system and what comprises of a thermodynamic system. So let us start with a study of what is thermodynamic system. Okay. So in the study of thermodynamics, we need to set aside a certain quantity of space which is considered distinct. So we need a space which is distinct, separated from everything else. Separated from everything else. Okay. Separated from anything else means anything which can influence it. So separated from anything that can influence it. Okay, so we need to set aside a quantity which is kind of distinct and separated from anything that can influence it. This quantity is called as your thermodynamic system, or simply we are going to refer it as a system. Now, every such system would be surrounded by some boundary. Okay, would be surrounded by some arbitrary surface, and this surface is called as your boundary. We are going to understand each of these terms in greater detail, but first let us understand what three things are important. Boundary and the region of space that lies completely outside boundary. So region completely outside the boundary is called as the surrounding of the system. Is called as the surrounding of the system. Okay, so these three are the things. So for example, what I want to suggest is you can go with this thing that let us say, so in general, let's say this is your system. Okay, this sets apart its what you can say, this sets apart its surrounding from the boundary, surrounding from the system. So this is, let's say, your surroundings. Let's say this is your system, and this will be your boundary. Okay, is that fine to you? So in general, let us take an example of what you used to take in your high school physics. Just give me a minute. Let us consider a gas-filled chamber that you usually take while studying the thermal physics. Basically, this is your gas filled in a chamber, and there is a weight supported by a sort of, I can say, piston or something, whatever you say, feel like saying. So this is your weight, okay, supported by a piston. Let us say this is your piston. Okay, I'll complete this piston. Okay, so this is your piston. Above is your weight. Now, this forms the boundary of the system. So basically, thermodynamics remains constrained at this space. So we are concerned about the thermal physics that will be going on in this particular chamber. So basically, this forms your boundary. This forms the boundary. Okay. So everything outside the gas, including weight, piston, all these comprise of what you can say as your surrounding. And this is one of the thermodynamic system. This is one of the thermodynamic system. This is one of the thermodynamic system. Okay. Now let us okay. So this is your thermodynamic system where you have a boundary and where you have this particular system, and then you have these other things apart from this gas. You can say everything outside this gas is your surroundings. So basically, piston, weight, and everything outside atmosphere all become surrounding. For example, I take another example of system of certain mass flowing through a pipe. Let's say this is your pipe. Okay. And let us say this is your AB, and this is, let's say, CD. And let's say water is flowing through this pipe. Okay, so let's say water is flowing through the pipe. Okay. In this case, you don't have a clear boundary, but here the boundary is imaginary. Okay, since water is flowing, so you know it is constrained to, so basically, this inside surface, this inside surface presents an obstruction to the flow of water, presents an obstruction to the flow of water. And this obstruction creates a boundary which is sort of imaginary. So there is, as such, there is no obstruction at the two ends. That is, at AB and CD, there is no such obstruction. However, this dotted line, which I'm going to present, this inner surface makes an imaginary obstruction to the water flowing, and therefore the boundary here is imaginary. And everything that lies outside this imaginary boundary is the surrounding. So all these things are surrounding. Is that fine to you? Okay, so these are some very basic things that we really need to understand. Now there can be differences in the chemical constituents, okay, or in general okay, because of some physical conditions. Okay, so there can be some differences also. So for example, uh, if a system, I'll write it here, if a system is completely uniform, is completely uniform with respect to with respect to chemical composition, chemical composition, and physical conditions, then we know that these systems are then called as homogeneous systems. These systems are called as homogeneous system. Otherwise, I will say these are heterogeneous systems. So otherwise, these are called as, if they are not uniform with respect to chemical composition and physical condition, then these are called as the heterogeneous systems. Okay, so other way of saying it will be heterogeneous system. Okay, for example, air, if it's not polluted, then obviously this air is the mixture of nitrogen oxide, carbon dioxide, oxygen, etc. If it's not polluted, then it some trace gases, etc. So if it is not polluted, okay, whether you test it here or somewhere else, its composition would remain the same. Okay, so in that case, I can say that this will be a homogeneous system if it's not polluted. But if it is polluted, let's say right now the air of Delhi would be different than air of Udaipur. So basically, then it will be a heterogeneous system. But otherwise, if I'm saying that if it was in the plain normal conditions, and let's say we are ignoring the geography of it, for example, if we are not moving to a beach or somewhere else, so basically, if we are in the same city and almost in the same geographical conditions, the air would be a homogeneous system. Okay, now let us come to an important aspect of thermodynamics, and these are open and closed systems. So basically, now we have studied system, we have studied boundary, and then we have studied what what is called as your surrounding. So anything that lies outside the boundary are called as the surrounding. So let us first discuss what is the system. So system can be of two types. One can be closed system, and another can be open system. So you can have two kind of system: closed system and open system. Okay, so closed system consists of fixed mass. Sometimes it is also called as technically controlled mass. That is, in this case, no mass can cross the boundary. However, energy and volume, energy can cross the boundary, and there's no restriction of volume. Volume may change. Okay, so volume need not be fixed. So such systems are called as your need not be fixed. So such systems are called as your closed systems. Is that fine? Need not be fixed. So for example, if you have a gas enclosed in a cylinder, fitted with a piston, so let's say this is a weight, fitted with a piston. Now, in this scenario, you know that mass is not exchanging, but volume is changing when you push the piston down, and then this gas exerts a pressure above. So volume may change, but mass is controlled. Mass is controlled. So in such systems, you can write that system is characterized by a mass constant or control mass. You can have an interchange of energy, but you cannot have a interchange of mass. Okay. Now, on the contrary, in open systems are those which have a fixed volume. So I can say an open system is a kind of properly selected region. It is a selected region where you can have a fixed volume. Basically, you can have a fixed volume here. Okay, and here both mass and energy can cross the boundary. So both mass and energy can cross the boundary. Okay, so such systems are called as the open system. So open system in which you can have an interchange of mass through the boundary and energy also. So for example, if we have this, what I can say, system of water heater. So in a water heater, um, I'll write it here. So let's say if I'm considering an example of water heater, if I'm considering example of water heater, so in water heater, you have this control volume only. Okay, so this is your water heater. You have an inlet here, you have an outlet here. So this is your inlet, this is your outlet. Now you have in this water heater, what is happening? This volume is constrained. So you have a control volume here. Okay. Now, since hot water will move outside and this hot water will get replaced by cold water. Okay. So it is not convenient to choose a fixed mass, but we can focus our attention to the volume. So whatever volume would be constrained, this volume in which water is there, this is fixed. You have a fixed volume. Okay. So basically here we can consider that some mass is entering and some mass is leaving. Some mass is entering and some mass is leaving. So cold water as a mass is entering and hot water as a mass is leaving. However, in this entire scenario, in this particular heater, the volume remains constant. So therefore, this forms an example of open system. Now, there are systems which are neither open nor closed. These are called as the isolated systems. So what are isolated systems? Isolated systems are those uh, in which you have no interchange of, you have no interchange of energy. No interchange of energy with the surroundings. So if you have no interchange uh, of energy with the surroundings, then such systems are called as your isolated system. Example, your thermos flask, sorry. Your thermos flask, ideally, is an isolated system. Now let us consider another thing which are called, which we've been studying, till now we have studied all these systems. Now let us study about boundaries. So number one, diathermal boundary. So these are all terminologies that I'm writing. Okay, so diathermal boundary is one in which heat can flow between the system and its surroundings. So heat can flow between system and its surroundings. So in this case, heat can flow between the system and surroundings. Such boundary would be called as the diathermal boundary, or this is a thermally conducting boundary. Thermally conducting or diathermal boundary. And in this case, you can say that system is in thermal contact with the surrounding. Second kind of boundary, for example, your normal tea. Okay, so tea is kept in uh, your cup, and now you know that it is going to exchange heat from the surrounding. So basically, exchange as it comes with the thermal contact with the surrounding, it is going to take the temperature of the surrounding and it will slowly become cold. So basically, because of thermally conducting boundary or diathermal boundary, this kind of exchange of heat between the system and surrounding take place. Now, second is adiabatic boundary. So what is your adiabatic boundary? Adiabatic boundary is such where your heat not allowed is not allowed to flow across the surrounding. So basically, delta Q is zero between the system and surrounding. Between the system and surrounding. For example, your thermos flask. If it is like in all sense, it is right. In all sense, it is nicely fitted, and then the boundary. This forms an isolated system. This you already know. This forms an thermally isolated system, and the boundary of a thermos flask is an adiabatic boundary. This is termed as an adiabatic boundary. Okay, then we have something called as a rigid boundary. Then we have something called as a rigid boundary. So if a boundary is such which cannot be moved, boundary cannot be moved. Okay, so if it cannot be moved, means you cannot compress the system, nor you can expand the system. So boundary is such which is rigid. So neither you can compress the system, nor you can uh, compress the system. So such boundaries are called as rigid boundaries. These are in general ideal cases. These are idealized. They cannot be achieved in practical thing. Okay. For example, if you have a heavy kind of heavy spherical ball, with a huge density, let us say very huge density of mass inside, huge density, okay, huge mass density, and this is very heavy, practically very heavy, then we can approximate this boundary as a rigid boundary. Then we can approximate this boundary as a rigid boundary. Only approximate as a rigid boundary. However, it is not. Okay. So in general, I can say that rigid boundaries don't exist. Okay. Rigid boundary don't exist. So ideally, rigid boundary don't exist. These are just some concepts that I'm writing. Now in chemistry or somewhere you write something called as permeable boundaries. So if a boundary allows an interchange of or exchange of mass, so if boundary allows exchange of mass or matter, I should write better, then these are termed as permeable. Okay, and then there are some other boundary like which is some semi-permeable. So basically, if we design a boundary that it only allows a certain kind of matter and does not allow certain kind of matter. So basically, if we design certain boundary which permits some components to pass through and stop others, then such boundaries are called as semi-permeable boundary. Such boundary are called as the semi-permeable boundary. So, for example, there is a boundary called as, if I design a boundary of hot quartz, then it stops all other gases except helium. Okay, so such boundary are called as the semi-permeable boundary because it allows some component to pass and some component to not pass. Okay, is that fine to you? Okay. Now, let us focus our attention to um, something very important, which are called as the thermodynamical variables. And as we go along, we're going to see them in greater detail. But let us first define them and define two of these important thermodynamical variables. And then we will go on to something called as the two more important concepts. Okay. Intensive and extensive variables. Okay. So in thermodynamics, a system is described by specifying its physical properties. So basically, what we do, if we are considering only thermal physics right now, let us say just consider thermal physics. Okay, so what are those physical properties? So whenever we study thermodynamics, we specify certain physical properties. So these are physical properties when we are considering a thermal system. This will be pressure, this will be volume, and temperature. Okay, so for example, any state, if I have to define a state of gas, if I have to define a state of gas, what do I need? I need to define three things. I need to define pressure, I need to define volume, and I need to define the temperature. Okay. Similarly, if I have a stretched wire, I need to define two things, that is length and tension. And if there is, let's say, some change in temperature, then temperature also will be another thermodynamical variable. So these physical properties in which I'm characterizing my state of the system are called as the thermodynamical variables. So these are my thermodynamical variables, or in general, thermodynamic variables. If I'm okay, so let's say we have pressure, volume, temperature is thermodynamical variable which defines the physical property of the gas or simply the state of the gas. Okay, the value of a property uh, which uniquely defines the state of the system, uh, you can say, is always kind of fixed. So basically, if I'm saying that uh, okay, so basically what I want to say is that that these define the state. Okay, so pressure, volume, temperature, and they are basically fixed. Okay, so they're basically fixed at a particular instant. So basically, if at a particular instant I'm measuring, then they are fixed. Okay, so what I want to say, I would write the value of um, these property. Okay, now so value of a property. Property means these physical property. I'm saying the value of physical property uniquely defines uniquely defines the state of the system and remain fixed at a particular instant when they are measured. At a particular instant when they are measured. For example, if I'm considering let's say system in which gas is filled. Okay, so obviously this volume is fixed at this particular instant and pressure is fixed. Okay, at this instant. Then if I apply some piston to it, obviously volume is going to decrease, but pressure is going to increase. Okay, so this particular values of P and V, this particular value of P and V uniquely defines the state, the present state. Okay, basically these properties can be assessed macroscopically, and therefore these are called as the macroscopic properties. These are called as the macroscopic properties. And what goes inside, like for example, this you'll study in kinetic theory of gases. So for example, pressure of the gas. So whatever pressure a gas is exerting on the wall, so pressure of gas, uh, pressure of gas exerted on wall. So basically it is nothing but it is the average rate of change of momentum. Average rate of change of momentum per unit. Average rate of change of momentum of, you can say, gas molecules, or average rate of change of momentum due to gas molecules per unit area. Per unit area of the wall of the container. So basically, pressure of the gas, we see it on macroscopic realm. So we see it on the macroscopic level. We see something called as pressure. But this physical property is intricately connected to average rate of change of momentum due to gas molecules per unit area of the wall of the container. Okay, in which the gas is filled, basically. Okay, so this properties is the microscopic properties. Okay, so these properties are not directly perceivable, but these are responsible for these microscopic observation. For example, temperature. So if it is an ideal gas in which we don't have any interparticle, or you can say intermolecular interactions, then the temperature of gas can be related to average kinetic energy. Average kinetic energy of translation of gas molecules. Translation of gas molecules. So basically the temperature is a macroscopic quantity in this scenario, and this forms your microscopic picture. So this forms your microscopic picture. Now let us consider something called as intensive and extensive variables. Intensive and extensive variables. So the first thing comes up in mind is, let's say if I have a system, A, and if I subdivide the system in two parts, if I subdivide the system into two parts, or basically expand the system, okay, let us multiply the system. If I subdivide the system or multiply the system, there would be some properties which will be impacted. Okay, so those variables which have the same values, which have the same values when the system is subdivided or multiplied. When the system is subdivided or multiplied are called as the intensive variables. Otherwise, they are called as the extensive variables. Okay. So for example, if I subdivide it, what has changed? The volume has changed. Okay. So volume has changed. Okay. If I subdivide it, so for example, if A is subdivided, initially volume was something else. Now volume is something else. Okay. If it was containing some mass of gas, so mass of these compartments would be different. So basically mass. So I can say that mass and volume are extensive variables because they depend on the on whether their values depend if their values change if the system is subdivided or multiplied. While temperature remains the same, so temperature is an intensive variable. In fact, whatever pressure it is exerting on the wall, that also remains the same. So pressure and temperature are intensive. We are going to list a few of them, a few more of them, and then in due course of time, we are going to really see, and we are going to really discuss whether these are intensive or extensive. So you have to remember one thing, that the intensive variables, one very beautiful characteristics of it is that intensive variables are independent of mass. While extensive variables depend on mass. Another thing that you need to really know, there will be a term which will called as chemical potential that we lately study when we are going to study Gibbs free energy and all those things. Density, viscosity, resistivity. You have something called a specific heat capacity. You have something called as pressure. And in magnetic system, we'll have something called as magnetization. These are all the examples of intensive variables. In fact, temperature is one other example that I've already listed. Now, mass, momentum, okay, entropy, volume, these are all extensive variables. In fact, another term we'll later study, which is Gibbs free energy. These are all extensive variables. These are all extensive variables. I hope it is clear. Okay. So for example, if we are considering gas in a cylinder, so pressure, volume, sorry, pressure, temperature, pressure and temperature, these are intensive variables. These are intensive variables. And mass and volume are extensive variables. In fact, density also happens to be an intensive variables. Okay, so basically density is mass over volume. Mass and volume individually are extensive, but density is intensive variable. I'll ask you why in the next lecture. If I'm taking an example of paramagnetic system, so in paramagnetic system, magnetization is an extensive variable. I've already mentioned magnetization is an extensive variable. However, the intensive variable is magnetic field, or flux density. Magnetic flux density, I should write better. So magnetic flux density B is intensive, magnetization is extensive. Okay. Okay. Now, state of a system may be completely identified by knowledge of some of its properties. For example, we were discussing the state of gas, so it can be identified by PV and T. So basically, the state of a system may be completely identified from knowledge of some of its properties. Because values of all the remaining properties can be obtained using these known properties. So for example, um, if we know pressure and volume and let's say number of moles, okay, from this we can always obtain temperature. Specifically of an ideal gas, if I'm speaking, if I know these properties, that is pressure, volume, and number of moles, then temperature can be obtained, right? Isn't it? So this can be obtained from this equation, PV is equal to nRT. And this equation, we are going to write it as this, we are going to term it as equation of state. This is something called as your equation of state. Okay. And it is the relationship between what? Pressure, volume, number of moles, R is a gas constant, and temperature. Okay. When the system has attained an equilibrium. So when system is at equilibrium with certain constant values of pressure, volume, temperature can be obtained. If you know pressure and temperature, volume can be obtained. So this brings us to a question of equilibrium. So equilibrium can be of three types. It can be of thermal equilibrium. It can be a mechanical equilibrium, or it can be a chemical equilibrium. You can have three kinds of equilibrium. You can have a thermal equilibrium, mechanical equilibrium, and chemical equilibrium. Okay, so if you have some water, let's say at 60 degrees Celsius in a container, and if the container is left on the table, after some time, water in the container would interact with the room surroundings, and it attains the same room temperature. Now, no further heat would move across. Such kind of equilibrium is called as the thermal equilibrium. So hot water, if I'm placed, hot water placed in a cup, and that cup is placed in the room. So obviously, and let's say this is the boundary is thermally conducting of the cup. So basically, what will happen? It will lose its heat to the surroundings, and let's say the surrounding temperature is, let's say, 25 degrees Celsius, and initially, let's say, cup temperature was 60 degrees Celsius. Now, after a while, both surrounding temperature and the temperature of the contents of the cup will remain the same, and we'll say that the contents of cup are in thermal equilibrium with the surroundings. So this is called as your thermal equilibrium. Mechanical equilibrium, you all know from your standard 12th, you know, if the net sum of the forces on the system or net torque on the system is null vector, then we say that system is on the mechanical equilibrium. So there is no such unbalanced forces or torque. If there is no such unbalanced forces or torque, then the system is said to be mechanical equilibrium. And let's say your battery system in which you have certain chemicals. Okay. So a system may contain some substances which may react chemically. After a while, all these possible chemical reaction cease. Okay. So when all possible chemical reactions cease, okay, then the system is said to be in chemical equilibrium. Then the system is said to be in chemical equilibrium. I hope this is fine to you. Okay. Now, when any of the thermodynamical variable associated with the system undergoes a change in its value, we say that a process has happened. So that process is called as the thermodynamic process. So such process is called as the thermodynamic process. So what is a thermodynamic process? When any of the thermodynamical variables undergoes a change while going from one equilibrium state to another. While going from one equilibrium state to another, we say that a thermodynamic process has been executed. A thermodynamic process has been executed. Okay, so this terminology is called as a thermodynamic process. For example, expansion of a gas. So expansion of a gas kept in, let's say, constant pressure. Kept at constant pressure. So expansion of gas means volume is increasing. So volume must be increasing because of some temperature. So expansion of gas has a constant pressure due to some heat. If heat is provided to it, so obviously it is going to expand. Okay, so initial state is something, and now let's say heat is provided to it, so it will change to some another state. So you will have another P and V to characterize it, P final, V final, and it would be P initial and V initial. So this is termed as your initial state, this is termed as your final state. And so basically you are moving from one initial state to another, one state to another. So you need some initial variables and then you need some final variables. So basically your thermodynamic variable here in this scenario where your temperature is, T initial and T final. So sorry, no, pressure is kept constant. So pressure is kept constant. Now, as you're giving some temperature, volume is increasing and temperature is also increasing. So basically now you can characterize your initial state by some set of variables. You can characterize a final state with some set of variables. So basically now you're going from some initial equilibrium state to another equilibrium state. Okay. So we say that a thermodynamic process has been executed. So here the thermodynamic process is expansion of a gas at a constant pressure due to heat. So let's say if I'm from one equilibrium state A, if I'm moving to another equilibrium state B, okay, so I can join these points via some different paths. Okay, so such graphical representation of a thermodynamic process is called as a path. Okay, so graphical representation of a thermodynamic system is called as the path. Now in the next lecture, we are going to study reversible process and how do we understand what is a reversible process. Till then, take care. Please let me know if there are certain doubts in this lecture. I hope you're learning well from this lecture. Take care.